All right, the final talk of the session will be given by Juan Galvez. He's a postdoc here at PPL, and he'll be talking about Charm++ and Python.
Okay, so thanks for the introduction. So yeah, like Sanjay said in his introduction, so this was kind of like a side project I started, and then I've been working on and off on it, but we've already made like really good progress. There's a lot of features. Also, Kartik, a member of our group, has also contributed. So, okay, so first I'll start with saying what is Charmpy. So it's a new distributed parallel programming framework for Python. It is basically Charm++ for Python. So it's high level, it's general purpose. It runs on top of the Charm++ runtime. So that gives good performance, good runtime performance. Also, we're doing a lot of optimizations at the Python level. And because it's Charm++, we get all those adaptive runtime features like asynchronous remote methods, dynamic load balancing, and automatic communication and computation overlap. So why Charmpy? Why are we doing this? So here are some reasons why we're doing this. So Python plus Charmpy is like it's much easier to learn and to teach and use than Charm++. There are many productivity benefits, as I'll show. It's also an opportunity to bring Charm++ to the Python community, obviously. So we looked at like what frameworks, what solutions are there in Python to do parallel programming. And it turns out that there's not that many. So like if you want good performance, you probably have to use MPI, the MPI wrappers for Python. But then that's not exactly high level. And then there are like high level frameworks, but they're slow, or they're not very scalable. Also, this is an opportunity to benefit from the Python software stack. There's a lot of popular libraries like for big data, for machine learning. And there's a lot of talk lately of bringing data and HPC closer and convergence and all of that. So this seems like a good opportunity to use all of that Python software and with an HPC runtime. So what about cons? So there might be other cons, but like from a general perspective, and if you're starting from scratch, obviously, performance is potentially an issue. But I want to show that it doesn't necessarily have to be. So you can actually get performance that's similar to C++, and I'll talk about that during the presentation. So right now, I'll go through some of the benefits you get from using Python and from using our new Charmpy framework. So one obvious benefit is productivity. So with Python, you typically do things with much less lines of code. It's higher level. It's easy to debug. Like you always get nice error messages, and you stack trace. You don't have to manage memory. In the case of Charm++, like you don't have to worry about serializing objects when you're sending messages. So Python can automatically do this, which means you don't have to write pub routines. You can customize serialization if you want to, but by default, Python is capable of serializing any objects, or most objects. And yeah, like I said, with Python, you get easy access to all these libraries like NumPy for scientific computing, pandas, TensorFlow, many kinds of libraries. So what are Charmpy specific features that we're providing? So one is that it simplifies Charm++ programming a lot. So the API is much simpler, more intuitive, as I'll show. And also, a good thing is that there's no specialized languages here besides Python. You don't have to pre-process or compile anything. So like Neil said, there's a lot of problems with CI files. And one benefit is here we don't need CI files at all. So using Python, metaprogramming, reflection, introspection, we basically avoid the need for CI files. Okay, so now I'm going to show like what a program looks like. This is a hello world. This is a complete Charmpy program. So you can actually run this. And So here what's happening, so your char, your distributed objects, if you want to distribute the object, you define a class, and you say that it inherits from char. And that's basically it. In your main function, which is like the main char, which is here, you're saying, I want to create a group of these chars, which creates an instance on every PE. And then you're doing a broadcast. This is just a regular method invocation. And the good thing is that you can send whatever you want. You don't have to declare types, number of arguments. You just send here, I'm sending a list of an integer, a float, and a string. The chars will receive it here in this say hi method. They'll print their method, they'll print the values they received, and then they're doing an empty contribution. This is a reduction, where basically when all the chars are done printing their message, they do a reduction, and this method will be invoked on the char element 0. And this will exit the program. So like I said, you can actually run this. To run it, you just do charm run or whatever on your supercomputer to launch the application. Instead, the executable is the Python interpreter, and this is the program. And you get the output. The output could look something like that. So yeah, very simple, as we can see. So here, I just want to show like how the overall architecture looks like. So you have your Python application, just any regular Python application, well, written, of course, for using the charm model. You import the Charmpy module. So the module, this is the runtime at the level of Python. We have like an interface layer which communicates which interfaces with the actual Charm++ runtime system, which is compiled as a library. So here I'm showing like 3 different components. They are just different implementations of this layer. Like we started with this one, which was the slowest, and now we transitioned to this one, which is the fastest. So Python is a technology that actually can compile Python to C. So this is C code, which interacts with the Python interpreter at the C levels, which allows for much faster implementation, obviously. And we are also starting to transition parts of this module to Python. So we're starting to get really good performance. And then at the level of Python, well, you can do anything you would do with your Python application. You can access any kind of Python libraries, technologies. You could even access C, C++, OpenMP code if you wanted to, using several technologies that are available. So this is like the overview of the system. Okay, so now I want to answer or give some pointers about, because people might be wondering, what about performance? Isn't Python really slow? And so, I mean, over the years for HPC, there have been a lot of languages proposed, like high-level languages, and apparently they're acceptable because they're compiled. And I think the trick here is to just use Python the same way. So this means that you're using Python to express things in a high-level way, but Python is actually driving machine-optimized native code. So that's the way to do this if you want performance. I mean, you don't want things to actually run in Python in the interpreter all the time. So there are some solutions here that I listed. There are probably others. But for example, well, you have the very popular NumPy scientific computing library, which is for arrays and matrices. So it's a really very nice API, but things internally run natively. And they access popular libraries like BLAS and LAPACK. Then you have Numba, which I'll talk a bit about this, which is capable of JIT compiling Python math and array code to machine optimized code. And then there's Python, like I mentioned, which can compile any generic Python code to C. This doesn't automatically give you super performance. I mean, but you have to couple it with C types. But it is potentially you can, if you use it right, you can get very good performance. So like I said, I want to spend a minute talking about Numba because, well, I think it's really cool, very, very easy to use, and and gives very good performance. So it basically takes Python code, compiles it to native machine using the LLVM compiler. It's specifically targeted more for like loops and array code. So I took this from their website. Here you have like a sum over a 2D array. So it's written entirely in Python. It receives a NumPy array here. This would be a 2D NumPy array. But it compiles it to machine code. And the only thing you need to do for it to work is just put this decorator on top of the function. And when the Python interpreter first encounters this function, it'll compile it. And from then on, it'll run as compiled code. So one feature which I encountered when I was using Numba, I thought it was interesting. I don't know like exactly what the potential is for it, but it's the fact that parameters for the application that would normally be treated as variables, they can be compiled as constants. For example, here if you have like this loop, and these are like application input parameters, which you don't know what they're going to be, so the compiler treats them as variables. Now, if you're using Numba, you can actually choose when the functions get compiled. So you could actually compile them after you know what the parameters are going to be. And then the compiler will treat them as constants, which might give it like room for more optimizations. And actually saw, like when I was doing tests, comparing this to the C++ code, that it actually produced faster code in some instances. So it was like a synthetic workload, so I don't know like what the impact would be in an actual application, but I thought it was interesting. And another thing you can do with Numba, which I haven't explored, is you can write CUDA kernels. So that might be an interesting thing to look at. Okay, so now going back to Charmpy. So here, your chars are just distributed Python objects. Like I showed, you just inherit from char. Otherwise, it's a regular Python class. Remote methods are invoked like any regular Python object, but just the difference is just using the proxy. Otherwise, the syntax is the same. Objects are migratable. The actual migration is handled by the runtime. All the Charmpy does is just serialize the object on one side and deserialize on the other side. Method invocation, like Charmpy Plus, is asynchronous in general. But you can also do, like if you want, you can do a blocking call, and the only difference is you put block true, which is an optional parameter of any entry method. To do this, you would have to mark the entry method where this happens at the call side as threaded, because the method in that case needs to run in a separate thread to pause, but the runtime will tell you if you need to do it. So if you use block without threaded, it'll tell you you're supposed to mark this entry method as threaded. So distributed collections, groups, arrays. If you want to create a group, you just do group of mychar, which you've defined previously. If you want to create an array, it's similar, but you do array of this class, and you give it the size and whatever number of dimensions you want. This would be a broadcast to the array elements, sending these arguments. This is a broadcast, a point-to-point message to a specific element. So, yeah, simple syntax. So for reductions, reductions have also been simplified compared to Charmpy++. Like for example, you call self-contribute, you pass the data you want to reduce, the reducer. Here you don't have to specify the type of the reducer. Like normally you're going to be passing NumPy arrays. You could pass in ints, doubles, list of ints, or NumPy arrays. The runtime will figure out what type to use. It will map it to the correct Charm++ C type. And this is the target of the entry of the reduction that will receive the results. So for custom reductions, it's easy to define them. They're just functions that receive a list of contributions, which are Python objects. And then inside you can do whatever you want with those objects. Like here it's doing a sum. but basically you can do whatever you want and just return it. I have it put here, but you have to, currently you have to register this function. And then when you call contribute, you specify your own custom reducer. One thing I forgot to mention here, I didn't include it, but basically when you call an entry method, if the object is local, is in the same process, the arguments are never going to be copied. They're just passed by reference. The message still goes through the scheduler, because I think it's a good idea to go through the scheduler, but it just sends a tiny message with a tag. Otherwise, there's no copying involved of any arguments between local objects. So now I'll show some benchmarks. So we ported a stencil code from the Charm examples to Python. So it's a full Python application. It's a 3D array of chars which send boundaries to the neighbors and apply a stencil code. And I ran this on Cori up to 128 cores on 2 nodes. So for all the array and math computation, I just put the numba.jit decorator so that it would be JIT compiled. And so these are the results on Cori. It's a strong scaling scenario. So it's comparing like the performance of Charmpy with the same exact code in Charm++, fully C++ code. So yeah, we can see the performance is like they're quite similar, especially at the beginning. Like here, Charmpy is just 1% slower. Here, it's within 3, 5, 8%. Here, the overhead of the Charmpy runtime starts to become more apparent. The time per step here is like less than 50 milliseconds. So that's where we're at currently. So I also wanted to show like how the performance has evolved since we started this. This gives roughly an idea. It's not exactly, because there are other things involved. But these 3 things basically represent like milestones in the project. We started with this interface, then transitioned to this one, and finally, right now we're in this one. And this is for the same experiment. It's just showing the relative difference to Charm++. So as we can see, like especially here, in this case with 128 cores, where it's very fine-grained, and the overheads start to become more apparent, so there's differences. But the performance has basically improved a lot. Here we're at 29%. Here it's like less than 10 using the Python layer. So I expect further improvements because I can definitely see room to improve things further. So I expect this will improve. So another.
You have purple for Charm, but that just means that.
Yeah, I mean obviously Charm is 0%.
Compared to Charm.
Yeah, compared with.
Like Charm takes 0 time.
Yeah, this is, it's relative differences. Yeah, yeah, exactly. So we also ported the LeanMD mini app from Charm++. It's similar to the NAMD force calculation. So Jim and David described this morning, so I'm not going to talk about it, but there's basically a spatial decomposition of atoms and a force decomposition for doing force calculation for pairs of atoms. So again, we ported it to Charmpy. It's completely in Python. The physics code and other numerical code, we just put the numba.jit to compile it. So these are results we got on Bluewater. So these are like, I think 2 months old. So they're not with the latest performance improvements. I expect right now they'll be better, but I didn't have time to integrate because this is on a separate branch. So they haven't been merged with the main branch yet. But basically we were getting like the difference was within 19% between Charmpy and Charm++. Okay, so now I have a couple more slides. These are more like a side note, but like people are wondering about how serialization works. So in Python, this is called pickling. like I said, Python can basically pickle almost any object. The user can customize just by defining these functions. The pickle module is implemented in C, and the recent version is really fast. But still, I wouldn't recommend like pickling your own custom objects. For built-in types, it's fine. But one thing we did is just like if you're sending NumPy arrays, we bypass pickling entirely. So the NumPy arrays are directly copied into Charm++ messages. So that way it's really fast. Communication is really fast for those particular types. Another slide, in case people are wondering, like, can we do shared memory parallelism with Python? Like, if people are familiar with Python, particularly with the most common implementation, which is called CPython. CPython can't run multiple threads concurrently. It can run threads, but not at the same time. So that's why we're using non-SMP mode to run Charmpy. Still, I don't know if it's a big deal or not. I don't think so, because outside the interpreter, you can still do shared memory parallelism, which means, like, for example, if you're using NumPy, and since internally it actually runs outside of Python, it can use multiple threads. Like the Intel Python implementation optimizes NumPy to use Intel threads and MKL. You can access external OpenMP code from Python, and Numba has a feature, I haven't tested it, but it can also do loop parallelization. So those are things to consider. And just to conclude, in summary, Charmpy provides an easy way to write parallel programs using the Charm++ model. I think the runtime performance is pretty good, and particularly now that we're writing critical sections of the runtime with Python. You can get high performance if you use these kinds of technologies like NumPy, Numba, or Python. Or if you want, you can interact with native code. And finally, you have easy access to these popular software stacks like SciPy and PyData. So thank you.
So can you show your example code?
The one at the beginning?
I'm really bad at coding, so this is the key slide for me. Like, I'm trying to see how much shorter it is than the C, CI, C++ .h version of the thing.
This is basically the only file you need, and you don't have to compile it or anything.
You don't have a CI file,
No.
a header file, blah,
Just
blah,
this
blah,
file.
blah, blah.
They-
Oh, yay. I'm so happy.
Thank you. Made my day.
See that what I was saying about the subjective measures of elegance. Some people would consider this to be much nicer and compared with the C++, and the C++ folk will say, but you don't get X, Y, and Z. So, but no, I had one narrow question, one broad question. Narrow question is, you showed a char array being created from a base class. So it looked to me like you could make a 2D or 3D array from that same class. And how does this index work? This index works correctly in that situation?
I actually showed it outside of, it's not really embedded in anything. Like, you could call this from the main char constructor or the main function, the main.
So when you say array equals array mychar 100, 100, that's a 2D array. So every member of it, if it says this index dot xy, it will get the first two dimensions. And whereas if I had created three-dimensional array of that same main char, this index will be different?
This index is a tuple of integers. Yeah, if it's a 2D array, it would be a 2 tuple. If it's a 3D array, it would be a 3.
Okay. And then the other question I had was, you didn't can you say something about, I assume, refers to Saurabh's question there, is that the leanMD and the stencil, did you compare the lines of code for Charm++ versus Python version?
We compare leanMD, but
that will be a
like
useful thing to put. You don't have to answer now, but that will be a useful thing to put.
The code was not final, so
talks.
I mean,
Okay.
we had to clean it up. So,
Okay.
Yeah.
So I use Python a lot for analysis of simulation outputs, and in fact, there's 2 floors up from where we are is Matt Turk's group working on YT, which is a Python simulation analysis package. I was just wondering, have you talked with them, and could you imagine sort of rewriting YT in, or something similar to YT in Charmpy?
I think YT uses OpenMP, so this for node level parallelization.
I think it goes across nodes.
So does it use MPI plus OpenMP, or what does it use?
Yeah, I'm not sure how it does across.
Okay.
Do you know, James?
So,
Yeah.
so on your performance comparisons, have you done any comparisons of what your library does versus, say, some of the other distributed Python libraries for stencil and stuff? Or have you just done it versus Charm++?
So, I mean, our initial exploration showed that there's not many Python libraries or frameworks for parallel programming outside of, you have MPI for Pi, but that's basically.
Right. Have you done a
MPI.
comparison versus MPI for Pi?
We haven't compared with MPI. I mean, MPI for Pi is just a wrapper for MPI, so it's like the performance is kind of, I mean, the results are expected. It's like comparing Charm++ with MPI.
Yes, but for people who do MPI for Pi, it will be a useful for people who use MPI for Pi, it will be a useful comparison, and then also useful to show how load balancing improves. Those are in some ways obvious points to you, but not to them.
Right.
Yeah, but so is the question like if we compare like low-level communication performance or like a whole application?
Both.
Both. Yeah, it'd be a good thing to do, definitely.
Yeah.
Yeah.
Could you go back to the slide where you were comparing your C types versus CFFI versus,
This one?
yes, yeah, versus Cython? Yeah, I'm just very surprised that C types has such poor performance, given that it is, for lack of a better word, more primitive than Cython, right? It has far less constructs than Cython does, right? I mean, it literally is mapping particularly like pointers into Python effectively.
So there are actually more things involved here than it's not really a comparison of these different technologies. It's really of how we're using them. So it's not like you can immediately say, but in any case, still C types is limited in the sense that it's an ABI interface.
Right.
So it doesn't generate any compiled code. So in that sense, it's slower than CFFI.
Yeah, but it doesn't need to, right? Because it's literally just passing pointers to typecasted internal NumPy representations.
There's a lot of overhead in that process. I mean,
were you using NDPutter for passing to C types?
using what? Sorry.
NDPutter. It's the NumPy underlying raw pointer type.
In C type? No, in C types, it's possible that in that layer we're not using it.
Okay.
But it's not the only reason. Like,
I was just very surprised because it's,
like I said, it's not really a comparison of those technologies, just on how we're using them. So we added more features here for direct copying of NumPy arrays. I don't think that made it into this layer. So
okay.
yeah.
All right, that'll conclude the session. So let's thank our speaker one more time, and we'll have a short break.